Hi guys. So we're going to work on section 2.7, the dilations portion of functions. Um, and basically, let's extend this. So just like when you think of the word dilation or dilating like the pupils of your eyes, a dilation means to stretch or shrink, mathematically called compressing the graph, either vertically or horizontally, or both. When you have a dilation, there are a couple different ways that you can think about this. Vertically stretching and vertically compressing. So the up and down portion, which is going to affect your y values. It's going to stretch the graph vertically if this a value is bigger than 1. On the other hand, if this a value is between 0 and 1, then it's going to vertically compress it or smush it together along the y-axis. A horizontal stretch, if you look here, that's something that's going to be located inside, and that's going to affect your x values. It's going to stretch the graph out on the horizontal axis if those values are between 0 and 1. Remember when I talked about everything on the inside is a little bit different or opposite, this is one of those things. This is kind of tough to wrap your brain around. If that number is bigger than 1, then it's going to horizontally compress your graph, which means kind of like push it together. If you took your hands and you push them together inward, that would be horizontally compressing it. So if you do that, think about like compressing the graph. If I draw a graph and I push this together, then basically these things are just going to kind of go like this. Like, I know I just changed it both ways. There we go. Okay, that's horizontally compressing it. So at the same time that something's being horizontally compressed, you can also think of it as going to get taller and skinnier, which is equivalent to a vertical stretch. So these two things kind of go hand in hand, a horizontal compression and a vertical stretch, a vertical compression and a horizontal stretch. Okay, let's get rid of this. All right, let's do some of these. Okay, so on your notes, you have a couple different things. So the first one says, it asks you if you have y equals 3, then the absolute value of x. So since this 3 is on the outside, the effect of that would be a vertical dilation. More specifically, let's try this again. So you have a vertical dilation, which would be, in this case, a stretch by 3. So when you think about that, it's going to get 3 times taller. So in purple, I'm going to graph this. Now remember that the normal graph for absolute value starts at the origin and it goes over 1, up 1, over 1, up 1. I'm just going to leave these black dots here to show you like the normal parent function. Okay, so if we're doing this one here in purple, the vertical stretch is going to keep it going over 1, but it's going to make it go up 3 instead of up 1. So it still starts at the origin, but I'm going to go over 1, up 1, 2, 3. Over 1, up 1, 2, 3. Okay, and I'm going to do that for as far as I can, and then on the other side of my axis as well. So left 1, up 3, left 1, up 3, over and over again. Okay, and then I can draw my graph. And what you can see is that your graph just became vertically stretched, and it's now 3 times taller. So if you look at these values that are at 1, they're now at 3. If it was at 2, it's now at 6 on the vertical axis. This next one that has y equals absolute value of 1/2 x, this is where it gets a little tricky because you have to use the reciprocal of the number that's inside. So if this shows me 1/2, in order to describe the effect, you have to figure out what's the reciprocal of this number. And the reciprocal of 1/2 would be 2. Okay, so this would be a horizontal dilation. And it's going to be a stretch because that number was between 0 and 1. Okay, so it's a horizontal stretch by 2. So instead of going over 1, I'm going to go over 2. So let's put my origin point. So instead of going over 1, like I said, you're going to go over 2, go up 1. Go over 2, up 1. So it's going to affect the numbers along the x-axis. Okay, so make that go in both directions. And then you can see that if you look at the black dots and you took the ends of the graph and you pulled them apart from left to right, then this is what the result would be. Okay, one thing to note is that these aren't rigid transformations. A rigid transformation keeps the graphs the same size, so they'd be congruent, they're just in a different location. All right, let's do some of these practice. So it's easiest to do these, guys, if you write down what each step is. So remember the order is that you have to do rights and lefts first. So this would be right 2. Then you have a vertical compression. I'm just going to kind of abbreviate here by a half. And then it's going to go up 3. Okay, so let's get our graph to where it's situated and we can see all those moves. Move this down a little bit. Okay, so we need this to go right 2, up 3. So let's start by putting our vertex point. So right 2, up 1, 2, 3, and there's our vertex point. And so instead of going over 1, up 1, we're still going to go over 1, but we're only going to go up a half. So now we're going to move over 1, up a half, over 1, up a half. And so you see it starting to flatten out. So now we need to do the same thing to the left. So over to the left 1, up a half, left 1, up a half. And we're going to keep doing that till we get our points on our graph. And then draw your line so that you have your absolute value graph. Okay, so again, that shows your vertical compression. So it's like somebody pushes on the top of this graph and flattens it out. Okay, the next one, we have several things. So if we go from the inside, we have moving left 1 space. We have a vertical stretch by 4. Then that lovely reflection, so we're going to reflect it over the x-axis. So now it's going to go down instead of up, and we're going to move it down 3. So the first thing I'm going to do is find my vertex point. So left 1, down 3. I'm going to put that vertex point right there. Okay, and again, this is a vertical stretch by 4. So this is going to move along the y-axis. So I still am going to move left and right 1. So I'm going to go right 1, but now I got to move down 4. 1, 2, 3, 4. Left 1, down 4 again. I can do one more of those. Left 1, down 4. And so you can see it starting to kind of get taller, if you will. If you want to think about it like that instead of shorter, that's what's happening. And then there's that graph. Okay, so on the next one, it shows a left 1 movement. I've already written these out. It shows a horizontal stretch, and the number on the equation says 1/3, but remember you have to use the reciprocal when it's on the inside. So that's by 3, and then it's going to move up 2. Okay, so go ahead. I want you to try to graph this on your own. So hit pause, try to graph it on your own. Remember, horizontal stretch means instead of going to the right and left 1, now you're going to go to the right and left 3 and go up 1 still. Okay, so hit pause, try to do this on your own, and then check your work in just a second. Okay, so here's the graph that you should have gotten. Remember that a horizontal stretch is going to end up flattening your graph out some. So my vertex is at -1, 2, and then I have room to put 1 point on the left and 2 points on the right by moving left and right 3s and up 1s. Okay, so we were talking last Thursday about how you have to protect the inside movement. So that means this thing right here has to be factored since you don't see parentheses around that inside move. So that's what I've done here on the right is I factored the 4 out, and so that keeps the negative on the outside, the 4, then parentheses x minus 1 minus 5. So the first thing that we're going to do is move this thing right 1. It's got to horizontally compress by 1/4. Remember my reciprocal rule. It's going to go over the x-axis and it's going to move down 5. Okay, so I think you're pretty good on everything except that horizontal compression. Let me talk you through it, then I want you to hit pause. Okay, in this case, you're going to horizontally compress, so I'm going to move, instead of right one, up one, I'm going to go right 1/4, up one, right another fourth, up one. So when you do this, right 1/4, up one whole, so then right basically 2/4 to go up two, right 3/4 in order to go up three, right one whole to go up four. So try that on your own, hit pause right now, and then come back and check it. So I didn't connect my dots yet to draw the actual graph because I wanted you to see where these line up so that you can see those 1/4 and 2/4 and 3/4 movements. Okay, so if you see that, I'm going to leave this kind of in yellow. Whoa, shut it. Okay, so when I connect this, there's my horizontal stretch, or sorry, compression. Okay, these last couple, you're going to write two equations, one that shows a vertical dilation and then one that shows a horizontal dilation that can represent each one of these. Because to be honest, like every single one that's a horizontal compression can be rewritten as a vertical stretch and vice versa. Okay, so the easiest ones to do, in my opinion, are the vertical ones. Okay, so if I look at this first one, and both of them are centered at the origin so that you don't have to worry about any reflecting, any left and right movement. I want you to focus on building a vertical dilation. So if I look, normally it would go over one, up one. Instead, this is going over one, up three. So as far as my vertical one is concerned, it would be y equals 3 absolute value of x. Okay, now this is also, again, remember that normally it would look like this. So that being the case, it shows that's a horizontal compression. Okay, so when we want to build our horizontal equation, we're going to have to put something on the inside. Okay, now this is showing that I have to go over like one, up 1/3, or sorry, over 1/3 to go up one, over another third to go up two. So if you think about, like, for instance, what we just did on this last problem, where it had a 4 on the inside and we were moving by fourths, that's going to show a 3 on the inside as well. So this is going to be y equals 3, absolute value of 3x, because this shows that we're going to be going over 1/3 in order to go up one. Okay, if we move along to number 6, or this last one over here, here's my origin. So vertically, it shows I'm going up 1 to go over 4. So that would be rewritten as y equals 1/4 x, with that inside my absolute value, that just the x. In order to do my horizontal, I'm going over 4 in order to go up 1. So this is also going to be a 1/4 x on the inside. So basically with the dilations, you just have to remember that these numbers are affecting that going over 1, up 1 type of ratio. And it's going to change. If it's on the outside, it's going to affect how many you go up, but you keep the moving over 1 the same. If you look at the horizontal one, the one where it's on the inside, that affects how many you move to the right or to the left, but you still go up 1 full space. All right, we'll talk more about this in class tomorrow. I'll see you later.